Today we're going to be going over the second of the third method that we're going to be learning to solve systems of equations. Recall that a system is a set of two or more functions, and our goal remains the same no matter what method we choose to solve. Our goal is to find the coordinate that the two equations, in our case, linear equations, have in common. So it's still the intersection on a graph. Picture-wise, it's just that we're not going to be graphing. So the second method is called substitution. Substitution is something that you guys are very familiar with. All right, back in probably even middle school, end of elementary school, you saw substitution for expressions like a plus b, and then they would tell you a is 2, b is -7. You would substitute the values in, and then you would simplify. Why do we need multiple methods? If I was looking at the example, our first example, y equals -2x minus 9 is pretty simple to graph. We start at -9, go up to back 1 since it's a negative slope. Remember, when we're graphing, we want to draw our line pretty accurately so we can see the exact point of intersection. When I go to graph the second line, however, I isolate y to get it by itself. And I'm just going to change that 19/5 to a decimal so that it's a little bit easier to graph. So 5 goes into 19 3 times. You have 4 left over. So that's 3 4/5, which is the same as 3.8. So when I'm looking at a y-intercept of 0.8, it's going to become a little bit more difficult to graph and a little bit more difficult to be precise. I'm able to get the whereabouts of where the coordinate is crossing, but it might not cut through exactly like it does for whole numbers through the coordinate. The other issue with the graphing method is sometimes you're going to get y-intercepts that are too large or too small and physically can't go onto the graph. So that's why we have a couple of different methods. So for substitution, our first job is to isolate one of the variables. And in this first example, we already have a variable that's isolated. Y is completely by itself. So that's going to be the piece that we substitute. It is saying that y is the same as -2x minus 9. So what I'm going to do is I'm going to substitute that box into the second equation. You always have to substitute into the other equation. You don't want to substitute into the same. So I'm going to plug my box in for y because it says y is equal. That's why I'm plugging into y. So now I'm going to substitute. I'm going to rewrite my second equation exactly how I see it. 6x minus 5. Here's the substitution piece. Instead of y, I'm going to place my box, -2x minus 9, and then continue to write the rest of the equation, equals -19. If you notice, now I have created an equation that only has one variable. It has the variable of x. In the prior equations, I was working with two different variables, and there's no way to solve when I have two separate variables. So I'm going to solve for x just like we've been doing all year long. So I'm going to distribute my -5 through. Combine like terms. Continue to solve using inverse operations, and x's value is -4. Now recall, our goal is to find a coordinate because at the end of the day, these are two lines. And we need to find where these two lines intersect at. So x is only part of my answer. So when you find one of the values, you're going to plug that value into one of the original equations to find the second coordinate. I always like to go back into the box because it's the easiest to simplify. So I'm going to plug in my x value of 4. So y is equal to -2. I now know x is worth -4 minus 9. And then I just have to use order of operations. -2 times -4 is 8. 8 minus 9 is -1. And the intersection of these two lines is -4, -1. In my second example, I have an isolated variable again. This time it just happens to be x, which is fine. So I'm going to box what x is equal to. So second step is to substitute into the other equation. The box is now going to be in place of where the x variable is, because it says x is equal to 2y minus 12. So I'm going to rewrite that first equation. I have 4. Here comes my substitution piece. And then I continue writing the rest of the equation. Minus 8y is equal to 24. I have created an equation with only one variable. That variable is y. So now I can solve for y. I'm going to distribute through. So I have 8y minus 48 minus 8y is equal to 24. My y's end up canceling when I combine like terms. And I am left with -48 is equal to 24. When my variables cancel out, like what just happened, it is a special case. -48 is not equal to 24. Therefore, our answer is no solution. That means if I were to graph these two equations on a coordinate plane, I would come up with a set of parallel lines, meaning they will never intersect, which is why there's no solution. In our last example, we don't have an isolated variable. It is easiest to isolate the variable with a coefficient of 1 or -1. So the first equation is going to be the easiest to isolate because there's only one step. It doesn't matter if you want to isolate x or y. They both have that imaginary coefficient of 1, so we're not going to have to divide out. It's just a preference. So I'm going to get the variable of y by itself. In order to get y by itself, I just move x over by subtracting it. Now that I have an isolated variable, I can box what it is equivalent to, and I'll be substituting in for y, since it says y equals, into the second equation. So I rewrite my second equation, 2x plus 2. Here's my substitution piece. Instead of y, I am putting in my box. And then I continue writing the equation equals 6. So I created an equation with only one variable of x. So now I can solve for x. I distribute through to get -2x plus 6 equals 6. Once I combine my like terms, my variables end up canceling. 6 is equal to 6. That is a true statement. So my final answer is all real numbers. Oops. or infinitely many solutions. Graphically, if I were to graph these two lines, they would be the same exact line resting on top of one another. So that means that they intersect at every single point.